Okay, now we are going to prove some important theorems from our module 2 in maths. Okay, so the first theorem here is that if you have a connected graph G, the connected graph G is a Euler graph if and only if it can be decomposed into two circuits. So this is what we're going to do. Whenever you see if and only if in a theorem, and if you want to prove this, we have to prove two sides. That is a condition here. That is, if a connected graph G is Euler graph, that is, first we have to see first condition would be like if the graph is Euler, then we have to prove that it can be decomposed into circuit. The second part we have to prove, like we can say that if you can decompose it into circuits, then you can say that the graph G is a Euler graph. So in two ways you have to basically prove. So in the first part, let's say if G can be decomposed into circuit, then I have to prove that G is a Euler graph. Okay, this is my first part. So first part is that I'm saying that the G can be decomposed into circuits. I'm saying it is decomposing into circuits. So in circuit means the starting and ending vertex are same. That means each vertex can have even degree, right? That means in every circuit, the key idea behind the circuit is that every circuit is contributing degree 2 to each vertex it is passing through. So if, let's say, G is a graph which is a union of its disjoint circuits, that means this G, let us say G, we have said that G is decomposed into circuits. So if it is decomposed into circuit, these circuits have no edge in common. If, let's say, if it is decomposed into, let's say, 3 circuits, so that means these 3 circuits would not have any edge common in that. That is what decomposition of a graph means. So if I am decomposing a graph G into different circuits, these circuits I am dividing this graph into a union. That means this graph G is considered to be what? The union of this edge disjoint circuit. Edge disjoint circuits means edge disjoint, I told you, edges are not common. So these circuits have no edges common in them. So this graph G is considered to be what? The union of this edge disjoint circuits. And since it is circuits, then every vertex appears in some circuits, right? Every vertex would be there in any of these circuits. So each circuit would contribute exactly 2 to the degree of any vertex it touches. So each of these circuit would contribute what? 2 to the degree to any vertex it basically touching. That is 1 to get in and 1 to get out. So the degree of every vertex in that graph G is considered to be even. So if the degree of every vertex in the graph G is even, means what? The graph is Euler. That is a Euler's definition. So that is, you can prove it. How you prove that? Proving of the part we have already learned, that if a graph is Euler graph, then the degree is even. That we have already proved, right? That theorem we have already proved. So here if you see, if you have a graph G that is a union of edge disjoint circuits, then that means that each of these circuits would contribute exactly 2 to the degree of the vertex it touches. To degree of any vertex it touches, 1 to get in, 1 to get out. So that means in that circuit, every that is, if you consider one circuit, in one circuit every vertex would be having exactly 2 to the total degree, right? Because circuit means that circuit would contribute degree 2 to each vertex it actually basically passes to. So each circuit would contribute exactly 2 to its degree, right, to the degree of any vertex it touches. So that means finally each of these circuit contains every that means finally if I'm taking the union of all these circuit, then every circuit would appear in some of the graphs, right? So that means every vertex in G can be considered to be what? Even. Because in a circuit every vertex would be contributing exactly 2 to the degree of the vertex in a circuit, right? And we know in any of the circuits, if you consider, every vertex would be present in any of the circuits, right? Every vertex would be present in there. It is there in some of the circuits. So that is one thing that you have to understand. So the degree of every vertex in G is even. So we can say that G is what? So by the theorem, we know that we have proved in our previous videos, we know Euler graph means what? Their degree is even. So the first part is done. Okay. So if a graph is decomposed into circuits, then we can prove that it is a Euler graph. The second part is that if a graph is Euler, then I have to prove that I can decompose it into circuits. That is my next part. So how do we prove the next part? So in order to prove this part, here if you see, you can consider that a graph G is Euler. So if a graph G is Euler, means that all the vertex in that is even. So let's say I am picking any vertex, let's say V1. So that V1's degree is what? That is what here we are saying. So we are picking up any vertex here. Here if you see, I am picking any vertex V1, and we know since it is a Euler graph, that vertex degree would be greater than or equal to 2. So that means there would be at least 2 edges at that vertex. And if I am traveling along these edges like V1 to V2 to V3, since every vertex, here if you see, since every vertex has an even degree, whenever you end a vertex, you can always exit it. So eventually you will return to V1. This forms the first circuit, let's say T. That circuit, if I am removing from the graph, I will get some other remaining graph would contain other even degree vertex, other vertexes, right? Still has all even degree vertices itself. That is, I'm just removing removing a circuit means what? Removing a circuit subtracts 2 from each of the vertices degree. That's it. What? So I'm removing that circuit, and still I have all the vertices to be even. So I'm repeating this, finding another circuit and removing it. So then you will get no edges. Finally you will be getting, after you have removed every circuit, means that you will have no edges remaining. So in this way the G can be decomposed into circuit. This is how G is decomposed into circuit. So here, so in this theorem, first you have to understand, that is the part 2. If I am explaining it again, I am saying the G is Euler. Euler graph means what? The vertices, all the vertices would have even degree. So that means I can enter to a path and they can exit from that also. That would mean I won't stuck anywhere. So if I am starting from V1, I can, that is V1 would has a degree greater than 2. So there would be at least 2 edges for one vertex, right? So I can exit from V1 also. So that means eventually I can return to V1, and therefore this forms a circuit T. And from the graph G, that circuit that we got by starting from V1 and traveling along the edges, because we know there would be at least 2 edges for one vertex. So I can get a circuit eventually by reaching to this V1 back again. And that circuit I am removing from this graph, and I have remaining vertices are all even degree itself, and I am keeping on removing, finding another circuit, and I am removing it again. Finally I will continue this until I am getting no edges. So that means when I go to graph G, which is a Euler graph, I finally decompose into different circuits like this. So this is how the part 2 is solved. So in order to do this, we are going to divide. So if I want to prove that in a connected graph G, if a graph is Euler, if and only if it can be decomposed into circuits. So first I have said that if it can be decomposed into circuit means what? Circuits can contribute, every circuit can contribute exactly 2 degree 2 to each vertex it is passing through. So that means every vertex, it is a connected graph, right? So G is a graph. G is a union of the edge disjoint circuits. So every vertex would be present in some of the circuit, right? In some circuit every vertex would be present. So each circuit would contribute exactly 2 to the degree of vertex it is basically touching. So that means the degree of the vertex in that graph would be even. So if the vertex degree is even, by the theorem which we have proved it before, we know that that graph is a Euler graph. So this is how we prove the first part. Now in the second part, we have said that the graph G is Euler, then I have to decompose into circuit. So for that we have said that if a graph G is a Euler graph, means all of its vertex has even degree. If all of its vertex has even degree, we'll pick any vertex, we will start moving from this vertex like v1 to v2 to v3. Since it has even degree, that means each of these vertex would have at least 2 edges in it, right? That is what even degree means. So you can enter one vertex and you can exit also. So that means you will get a circuit. Eventually you will reach v1 again and you will get a circuit. Let's say it's T, and I'm removing the circuit T from G, and I will get remaining some vertex would be there which is all even degree itself. Removing a circuit means I'm subtracting 2 from each of the vertices degree. That is what removing a circuit means. And I will repeat on removing the circuits until I found there is no edges remaining. So in this way I have divided the graph Euler graph G into different, I decomposed into different circuits. So this is how we are going to prove this theorem.